These next examples are going to use the Pythagorean theorem and its converse, and we're going to try to answer these essential questions with the examples that you're about to see. How is the Pythagorean theorem used? How is the converse of the Pythagorean theorem applied? Well, very straightforward to start out with. Solve for x. We've got a right triangle. The notation shows us a right triangle, so we know that the x is the hypotenuse. It's opposite from the right triangle, so that must mean that 5 squared plus 12 squared is going to get us our hypotenuse squared. So 25 plus 144 is x squared. 169 is x squared, and 169 is a perfect square. We're only talking about positive side lengths, so 13 is the missing side length. And actually that forms what's called a Pythagorean triple. 5, 12, 13 is a Pythagorean triple, those side lengths. Find the length of the hypotenuse of an isosceles right triangle with legs 10 units long. Well, if you're having trouble visualizing this, one option is to draw yourself a picture. See if I can draw myself a picture of an isosceles right triangle where the legs are each 10 units long. So here are your legs, here's your hypotenuse, we don't know what it is. Now 10 squared plus 10 squared is going to equal x squared. So what we're doing is we're adding the squares of the two legs. So this is actually 100 plus 100 equals x squared. So x is really the square root of 200, because in order to solve for x, we're going to have to square root both sides, and x equals the square root of 200. That's going to be our answer. Now, these answer choices, there is no square root of 200, but we can reduce this down. 200 is 2 times 100, and 100 is a perfect square, 10 times 10. So this actually ends up equaling 10 on the outside, 2 on the inside. Answer choice C. Okay, let's solve for x given this diagram. Now this is a more complicated situation. You can see you've got a couple triangles that you're dealing with here, a couple right triangles. In order to solve for x, which is a leg of this triangle with a base of 10, we can't use the Pythagorean theorem until we've figured out the hypotenuse here. Okay, we can't figure that out. We need to know that in order to figure out what the x is. So let's call this y, since we've already used x. Now how are we going to find y? You'll notice y is situated in a completely separate right triangle here, and is a leg of that right triangle with a hypotenuse of 15. So really what we need to first do is figure out that what this side length y is. So y squared plus 9 squared is equal to 15 squared. So that's going to allow us to solve for y. So y squared plus 81 is equal to 225, which tells us that y squared is equal to 144, which is a perfect square. Y must be 12. So here in our diagram, we go back here, this side length is 12. That's enough now to focus our attention on this bottom triangle, where that 12 is the hypotenuse, and the legs, the square of the legs, x squared plus 10 squared, have to equal our hypotenuse squared. So x squared plus 100 is 144. Which tells us x squared is actually equal to 44. We're going to solve by square rooting both sides. Given your answer choices, we're looking for a decimal answer choice. So we can put the square root of 44 into the calculator to solve this one. 6.6. Okay, a 20-foot ladder is leaned against the building so that the bottom of the ladder is 8 feet from the base of the building. How far up the building does the ladder reach? the building is perpendicular to the ground. So let's see if we can't draw ourselves a picture and try to understand this scenario. So we've got this building over here, right? We've got the ground underneath, and we've got this ladder leaning up against the building. Well, here's a right angle because the building's perpendicular to ground. What else do we know about the scenario? The ladder is how long? It's a 20-foot ladder. So this ladder is 20 feet. And how far is the base of the ladder? The base of the ladder is 8 feet from the building, so this distance here is 8 feet. And we want to know how far up, the height of the top of the ladder. So here's a Pythagorean situation where we know that the leg x squared plus the leg 8 squared has to equal the hypotenuse squared. So x squared plus 64, x squared plus 64 is equal to 400. And that tells us that x squared is equal to, try that again, x squared is equal to 356. Nope, 336, try that again. And again, the square root here is going to get us what we need to solve for x. Given your answer choices as decimals, we can plug that straight into the calculator. Square root of 336 is 18.3, about. Okay, tell whether the given triangle is a right triangle. What we need to do is try to identify which of these three sides is the longest side. Again, don't assume anything from the diagram. Just because it's drawn as if 3 root 34 was the hypotenuse, no assuming that. We've got to evaluate this for which is the longest side. So 3 root 34 is approximately what decimal value? It's approximately 17.5. So it is in fact the longest of the three sides. So that would be our hypotenuse if this were a right triangle. So we've got to test, does the sum of the squares of the other two sides, so 9 squared plus 15 squared, does that in fact, question mark, get us 3 root 34 squared? That would be our hypotenuse. So does 81 plus 225 equal, well, if we square the 3 we get 9, if we square the square root of 34 we get 34. So does 81 plus 225 equal 9 times 34? So this is 306 and this is 306. So the answer is yes, this is a right triangle. Okay, how about another one? Now there's no mystery as to which the longest side here is. 26. That's got to be the hypotenuse if this were to be a right triangle. So let's put these side lengths through our Pythagorean theorem to check. 26 squared should equal 22 squared plus 14 squared. And when we do the math, they just don't add up. And this is obviously not a right triangle. Okay, so let's classify the triangle with these given side lengths. Possibly right, but it could be obtuse or acute. So let's take a look. We're going to use our triangle inequality theorem just to make sure that this actually does represent a triangle. So the sum of the two smaller sides has to be greater than the length of the third side. So 9.5 clearly greater than 6.1. Fantastic. 4.3 plus 6.1 is definitely greater than the side 5.2. Likewise, the two longer sides are going to add up to something certainly longer than the shortest side. So good, this is a triangle. This does represent a triangle. Now, can we compare the square of the lengths of the longest side with the sum of the squares of the other two sides? So let's see that. our 6.1 is definitely the longest side. That's got to be the hypotenuse if we're going to talk about a right triangle. That's the longest side. And we're going to compare 6.1 squared to the sum of 4.3 squared and 5.2 squared. The sum on the right side of the inequality clearly larger than the 6.1 squared, and the result there, since c squared, the longest side squared, is less, then we're talking about an acute triangle. Okay, side lengths 15, 17, and 28. Let's try and figure out what type of triangle it is. Keeping in mind, one of our options is that this is no triangle at all. So we really want to check, do 15 and 17 add up to something greater than 28? Well, okay, 32 is certainly greater than 28, so good. This is a triangle. We're not going to consider it answer choice D at this point. So now do the sums. How do the sums of the two smaller sides compare, question mark, to the square of the longest side? Well, let's see what happens. So squaring these, we have 225 plus 289, and 28 squared is 784. So adding these together gives us 514, which is less than the square of the longest side, 28. So when the c squared length, when the c squared value is the larger than the sum, we're talking about an obtuse triangle. Okay, here we go again. Three new side lengths. Let's do a quick check to see, do the two smaller sides here add up to something greater than, try that again, do they add up to something that's greater than the third side? Definitely 46, yes. Okay, so again, this is a triangle, and I skipped over the shortest side only because the side lengths are fairly large and the numbers are all pretty close together, but you could check to see that the shortest side, 22, is greater than the difference here of the other two. I skipped that, but almost because it's so obvious here that 22 is greater than 7. But you would want to check that as well. You don't want the shortest side to be too short. So really now what we're after is, what do the squares of the two shorter sides end up being in comparison to the square of the longest side? So question mark, what's this? Well, 484 plus 576, oops, not equals, question mark, how does this compare to 961? Alright, 1060 is greater than 961. So the sum of the squares of the two sides is the greater value. That results in an acute triangle. Okay, last example. Here are three more side lengths. The first example that we looked at was obtuse triangle. The one we just did a second ago was acute. And well, let's just see what happens to this third example. No hints there. Well, again, here are two short sides, and they add to some value that's greater than the greatest. And our, just to check again, our shortest side is greater than the difference in the two longer sides. 20 is greater than 8. Okay, so we've checked to see, again, we're dealing with values that could be a triangle. What we want is the comparison between the squares of the two shorter sides. How does that compare to the square of the longer side? 400 plus 441, we're comparing to 841. Well, we end up with 841 on the left, 841 on the right. Wouldn't you know it, these are equal. That equality tells us this third example is going to be a right triangle.